Okay, here are a couple of examples from section 5.2 where we are going to take these Riemann sums that are written in kind of the Greek notation and change them to the Roman notation and the actual integral that we use nowadays. So again, here's a function, we can tell that this is a function because this is going to be the height of our rectangle. The value of the function at c sub k, which is some arbitrary point determined in each subinterval. Now the intervals are going to be regular for computational means because it's going to be a little bit easier, so we're going to call these delta x, but this will be a regular partition. So all these bases will be the same, that way we can factor it out, and we just have to evaluate the different heights and sum all these up. So the bases of all these rectangles are going to be the same, it's going to be delta x, but the heights will be different depending on the c sub k and its value determined by the function, which gives us the height of the rectangle. Okay, and we're going to sum up all these rectangles as the number of rectangles approaches infinity, so we're going to get pretty much the area under the curve from 1 to 7. So that's basically what this looks like, or what this is determining. Okay, height, base, this is actually the interval, and this is the summing them all up. So we just write that as the integral. Now remember, these will be my limits of integration, so I'm going to go from 1 to 7. And then all this is, again, kind of summed up into the integration sign. And then this is our function, which is going to give us the height, and this is the base. And as we sum this up, this delta becomes dx, just like we do when we take differential calculus. Delta y over delta x ends up becoming dy dx. Okay, so this is our function, so we can call it, in this case, we called it x. It could have been t, it could have been h. This is a dummy variable. So the function does 2 times something squared minus 5 times something plus 1. So we're going to call that something x, but like I said, we could call it u, we could call it t. So 2 times something squared minus 5 times something plus 1. So there's your function, and then this becomes the dx. Okay, so that's how we just transfer that from the Greek Riemann notation into the standard integral notation. With the d, this is going to be, inspired by Leibniz's notation. And we basically should say where n, because we're going from k to n here, is any regular partition of the closed interval 1 to 7. Okay? That means all these subintervals are going to be the same. That's why we could factor that out and not have a delta x sub k. Okay? Hope that makes sense. And one more, these are pretty straightforward. Just have to, appreciate the notation and what it stands for. Again, we're just summing up all these rectangles. And this is what we do call a definite integral, because we have a definite range of values. Okay, so again, this is we're taking the sum of all these rectangles. This is my base of all the rectangles. It's regular, so the base will be the same, and this heights will be determined by the value of the function at the c sub k, which is in each of the different intervals. There's a different one of these, so this is all going to be determined by the value of the function. And again, we can write this as the integral. And my limits will be from -2 to 5, so I'm going from -2 to 5. And again, all this is integrated into this integral sign. All this becomes the integral sign. And then this is my function, 1 over 4 plus something squared, so I'm going to call that something x, so 1 over 4 plus x squared. And this delta x becomes dx. Because we're doing the limiting factor. We're taking the limit. Okay? And this will be any regular partition of negative 2, 5. Okay, now there's just a regular partition. We can call it n because that's just going to be the number of rectangles we're going to be having. It's going to be approaching infinity. Okay, and my k starts from 1 and goes to infinity, so I'm summing up all these infinite number of rectangles. I'm going to get the area under that curve. Okay, so that should help you, and those are basically what we have to do on numbers 1 through 6 on your homework, so I hope that's pretty easy to do. Okay.